folks to be able to, one, learn more about resources, but two, it's for developers to be able to have enough information to be able to do what we all want them to do, which is to develop. So I'm going to put this in more practical terms. So where is the resource? So that's the location. How hot is it? That's the temperature. How much and how quickly does the fluid flow out of the resource? So the flow and the pressure. You know, if you have a resource 15,000 feet down, but you can't get to it, you know, you can certainly, and there are mechanisms for obviously moving fluid, but it sure would be nice if you could get some to the top without having to pump or do some of these other things. What sort of chemicals are in the fluid? The salinity, the gas, saturation, etc. How big and how long will that resource last? So that's going to have to do with the formation, the porosity, the permeability. And the good news is a lot of this information is known in oil and gas. So that these types of measuring these things, you know, these items have already, in many instances, been measured. We just think it's important that you understand that that type of measurement would be very important for geothermal as well. How do I get access to that resource? Meaning the wellbore. How do I get access? You know, how deep is it? Is it plugged? Is there still casing in it? Is it producing $25 million for BP, so there's no way I could ever get it? You know, what's the production? These types of things. And can I, and does it make sense for me to get access to it? And this is the stuff that I was talking about. You know, the production, the well status. As I say, all of this stuff is likely in, you know, the state's oil and gas records. It's just a matter of knowing that this is valuable. So I'm going to talk specifically about Texas, because that's where we've done the most work. But this, I think, will apply basically anywhere. So our data sources for all of that stuff is obviously, the number one is the Texas Railroad Commission, and we have, like I say, over 1 million wells. I think we've got about 1.2 million wells worth of data. The Bureau of Economic Geology, which is, you know, part of our group and part of the Arizona group as well. So they've got a large amount of data. Oil and gas companies, log libraries, papers. So we've basically gone through a tremendous amount of varying resources over the years and pooled as much relevant data as we can to answer these questions that I just said. And so I think that the key is going to be answering these questions. Let me go to the next one. So where do we find the data? I'm going to go through this reasonably quickly, and then what I'm going to do is the SMU group, we work together to actually get very specific. I'm not sure if everyone on this call has the material that we put together probably about 1.5 years ago that really details what exactly are we looking for and what is relevant beyond, obviously, temperature, which is, you know, valuable. So the first one is the resource type. And as I said before, this is really market-driven. So you need to know the resource that is most likely in your, you know, state. Is it hydrothermal? Is it, you know, EGS could, in theory, be anywhere. There are places that are more economic and less economic right now, but, you know, low temperature or geopressure. You know, there can be some other types of resources that are interesting, but I think that those are, you know, the 4 resources, and they're not mutually exclusive, but it's nice to actually know what you're potentially looking for. The second is geographic information. So where is the well? You know, where are we looking? So you're going to get that, obviously, from well headers, from surveys, and any type of digital map data that you have. The next important piece of information is engineering. Engineering data, meaning how large is the well? When they drilled it, how large was how large is the casing? Because if we know the size of the casing, we can predict, in theory, how much fluid could actually be produced. If we know whether or not the well is plugged, we can know, you know, is it going to cost us $1 million to unplug that well? So how valuable is that resource? So those types of things. And we can get, you know, wellbore data from headers, well test data, certainly from scout reports. There's a number of different pieces of the puzzle that you can actually pull from to get that type of data. the status is very, very, very important, because even if there is a great well that is very hot and could flow, if it's shut in, you know, you have to consider how are they going to get to it. Have they pulled out the casing? Because it could be very, very expensive for a developer to, you know, go back in. Or as I mentioned in the other example, if it's producing whatever, $10 million, $100 million for a very large oil and gas company, it's in the middle of a giant shale play. It's certainly nice to know for the developer that it's available, and maybe someday when that giant shale play ends, you know, geothermal could be a possibility. But it's important that we know whether or not, you know, as a developer, it's important to know what's the current status of that well. So production data is going to be very important to knowing that. From an infrastructure point of view, you may have a wonderful well, but you have no access to electrical lines. You have no access to pipelines. You have no access to basically anything. So again, it could be a feasible option, but you'd have to build into the cost all of these other expenses. So certainly in the state of Texas, we have, you know, pipeline GIS layers. We have, you know, and you can get a lot of this from Esri or things like that, topographical layers. There's resource layers. So any of that that's available from the state would be very, very valuable. Production and flow data. So this is, you know, this is really how much fluid is coming out of that well and how much water is coming out of that well. It's very, very hard to know, but if you know how much water is being disposed nearby and you know how much water is being injected, we've got some fancy calculations that you can put into place to say, you know, how much water is coming out of it. In the state of Texas, this is different than some other states, they don't actually tell you, you know, how much water is coming out of a well. So that is not a direct measurement. So you have to do some deductive reasoning to figure that out. In other states, you know, you may actually know exactly how much fluid is coming out, but injection and disposal data is very valuable, because if a developer understands that there's a tremendous amount of disposal going on in a particular area, they're going to presume that there's a lot of possible water there. So, and you know, if they know that people aren't injecting that fluid in, but they're disposing of it, that's a good clue that this might be an interesting area. Oil and gas developers will always try to keep away the water, but if they're still getting water, it's quite interesting, because that may be a place where you have a tremendous amount of flow that's available. Well test data. So in Texas, we have G10 data that basically tells us once or twice or sometimes 3 times a year what's happening in a 24-hour period. That's very, very valuable data. And production data, which I mentioned. So let me go to the next one. Obviously, heat flow. You know, I think that most people here are focusing a lot on heat flow. You know, they're basically working on, you know, bottom hole temperatures and this type of stuff, and that's very valuable. I think that that's the most obvious value, you know, that we can pull are the bottom hole temperatures. Any type of temperature tests. There are wells where temperature tests occur. Again, in our G10 tests here, once or twice a year, they actually measure the temperature at a given interval. So it's not only when they drilled the well, but there are other types of temperature tests and pressure tests, which is also very valuable, that occur several times a year. One thing to understand is that something happened when you drilled the well, and there's certain measurements, but that's not static. So over time, I mean, a well could have been drilled 25 years ago, and the Earth is you know, the Earth can change a bit. And, you know, when they drilled, they used mud, and it maybe that cooled it down. So if there are tests that occurred, you know, every year, a couple times a year, it's very valuable to give the developer that type of information so that they're seeing that information over intervals, not just what occurred when it was actually drilled. Geology can be well logs, drill stem tests. The red ones are very hard. So like the geochemical tests, the reservoir data, you know, this does exist. Most of what we've received in this actually comes from oil and gas companies. It's typically not stored I mean, certainly the BEG has some, but it's the hardest data to get. And then let me give you, I'm going to give you specifics. So this is, I just want to give you a very broad overview of the type of data that we think from oil and gas that is, particularly valuable for a developer. And then what I'm going to do is let me actually bring this over here. Hopefully you see this. Kim, can you just get on and unmute and tell me if you see this, that change? I'll assume yes. So this, Kim, do you?
I got it.
Okay, great. Thank you. So this is something that the SMU group put together that takes what it is that I said from a very high level and brings it into a very, very specific, what are the types of data items that are extremely valuable for geothermal that you can that you would want. So in an ideal world, what would you want? So what I did is I highlighted this. I highlighted the yellow ones, what it is that you can get from oil and gas. Some of them you're just not going to get from, you're not going to get business data. It's hard to get infrastructure data. I mean, you can get a little bit. It's hard to get geophysical data directly. I mean, you can get it. It's just very hard to get, typically from a state group because it's more analysis. Or seismic data is very hard to get. So I'm more than happy, to share this afterwards. And this is really, I don't want to, I want to open up the call here, but these are the very, very specific items that are valuable for geothermal development that you can obtain through oil and gas records. So basically, on this one, everything here, we would consider very, very valuable. And this one, it's just this, and that you can actually get access to. And like I say, I know some of the states' data pretty well. I mean, I know Texas really well. I know some of the other states reasonably well. But, I'm sure you guys know your own data quite well. And if you look through this and said, what do we have and can we match it up to this, I think that it would be quite valuable. So that's it. I'm happy to answer questions. I think somebody else pushes buttons, not me.
We're going to go ahead and we did have one request to post the table that you just showed on the state.
Sure, I'm happy to.
Yeah, we can definitely do that. We'll go ahead and I don't see anything else pressing right at the moment, so we'll take questions in a Q&A session, and I'm going to pass the presentation over to Will. And Will, you should be
okay. Yes, if you can hear me, what I'm going to do is walk you through what we've been doing for almost 30 years in North Dakota assessing geothermal resources, and most of this work has been done for DOE. So this is what we're after in the beginning. You want to be able to try to calculate how much energy is in the rocks and then try to figure out how you would go about getting it out and what volume of it, what amount you can get out, and so on. So, some of the things you need, and all of these things you will be able to get from the National Geothermal Data System. A lot of this information is going into the well headers on almost all the wells. So rock density, volumetric heat capacity, you want to know the volume of the rock, and you want to know the temperature of the formation and the temperature to which you can drop it. And this gets to be important when you decide, how you're going to use it, if you're going to generate electrical power or something like that. And that's going to be a function of the heat exchanger. Well, here's how we go about it. The first thing we do is we consider heat flow. And here we need to get two important pieces of information, the temperature gradient and thermal conductivity. We measure the temperatures in boreholes at usually constant intervals. I'm going to show you how we go about that. You can also derive the geothermal gradient from bottom hole temperature data. This is something that is becoming much better refined, a lot better than it was, say, 20 or 30 years ago, and we're doing a lot with that, and I'll show you a little bit about where we are with it. Thermal conductivity turns out to be very important, and when we first started doing this, like in 1984, the thermal conductivities that we had were just simply taken from the literature. We didn't have any really good measurements for the deep rocks in the various basins. Fortunately, we've been able to do a lot with that, and we're going to be doing a lot more with it in the future. You need to know a lot about the formation properties, and this is for production information, their porosity, permeability, thickness, the volume of the rocks, the overall depth. If you can create something like structure contour maps, this is really where you want to go, and I'll show you a little bit about how we get there. Heat flow is pretty simple. We calculate it using Fourier's law of heat conduction, multiplying the temperature gradient times the thermal conductivity. You can also calculate thermal resistance in the borehole, which uses the entire length of the data set. With Fourier's law, you usually end up multiplying some linear portion of the thermal gradient times the thermal conductivity from that part. And as we've seen in a lot of boreholes, the numbers can change down the borehole, not as a function of thermal conductivity, but as a function of some climate disturbance at the surface. Now, heat flow, there's a lot of data out there. There's going to be a lot of heat flow data on the National Geothermal Data System. We have mated the global heat flow data set with the SMU database, cleaning up a lot of information in there that was conflicting or had a lot of typos in it. It's been a really tremendous effort, and I'm really proud of all the people who've been working with that. Okay, here's a temperature log from the western portion of North Dakota, Williston Basin. Although I've smoothed it out a lot to get rid of the oscillations you get usually when somebody doesn't have the temperature recorded exactly right or the depth right. But this is a really good temperature log, and the characteristics you can see are that the thermal gradient changes with depth, and in this case almost everything is related to thermal conductivity, and that's why thermal conductivity gets to be important. When we measure temperature versus depth, this is a small portable instrument that we use. This one only has about a 600-meter cable on it, but it's been incredibly useful. It turns out that about 90% of all heat flow measurements in North America are in holes less than 400 meters deep. And this is where the bottom hole temperature data set is going to come in, because here we have data that goes to tens of kilometers in some cases, but a lot of data in the 2 to 4 kilometer range that really hits the area where the rocks are hot enough to be useful. We make thermal conductivity measurements on samples we get. We're very fortunate here in having a tremendous core and sample library right across the street, and we have measurements going on continuously as we get core samples from them. The instruments look like this. We can actually duplicate the in situ conditions, so we can put the rock samples at the temperature and pressure they exist in the ground, and this turns out to be relatively important. And then we apply a technique we've called thermal stratigraphy. We simply apply Fourier's law of heat conduction, and then we calculate the temperature at depth as a function of the heat flow, the thermal conductivity, and the thickness of the sedimentary layer. And I just wanted to show you a little quick peek of what the Williston Basin looks like, where it is overall. And here's some of the thermal characteristics. On the left, we have the thermal conductivity profile, and this turns out to be very important. Very low thermal conductivity in the upper portion of the basin, which consists largely of clastics, tertiary and Cretaceous clastic rocks. The pure shale is particularly thick. Once we get into the Paleozoic, the rocks are carbonates, and the thermal conductivities are a lot higher. And if you look over on the right, I have 4 plots for temperature versus depth based on different heat flow values. You can also see the very characteristic change in thermal gradient as a function of thermal conductivity. And this is where heat flow, as you can see, is going to be very important. If heat flow is low, you have relatively low temperatures at depth. If it's high, you have very high temperatures. And there's a tremendous difference in this case. When we first started, we did not have thermal conductivity measurements, which I mentioned right at the beginning. So we took data from the literature, and this is an example of how we came up with general stratigraphy for the Williston Basin. We had information on formation thickness, and we really didn't have anything other than surface temperature. So we were able to project, just based on what we knew about the basin overall, what the temperature would be. And if you look on the far right, you see the gradient in degrees C per kilometer. Notice how it changes. And again, that's just a function of the thermal conductivity. Now when we step forward and see how we're doing it today, it's a lot different in this sense. We've been making thermal conductivity measurements for the last 3 years now, and there's some dramatic differences between what was in the literature for generalized rock types and what we actually have in the basin here. And if you look over on the right, you can see the percent difference in thermal conductivity we got from data we had that was published in 1981 and what we're seeing today. Sometimes we have higher thermal conductivities, sometimes we have lower conductivities. And here's how it works out. Temperature depth plot calculated just simply on stratigraphy, assumed constant heat flow, and putting in the conductivities. And you can see at the bottom with our new conductivities, we're actually coming up quite nicely with higher temperatures than we had with the older conductivities. And this is just simply calculating based on heat flow. And I wanted to run through the general stratigraphy of the basin and what we have. And if you look on the far right side, you'll see the thermal conductivity that we have inferred from the rocks in these general sections. And here's a whole section of Cenozoic rocks for which we really have no measurements of thermal conductivity. We've inferred these based on the thermal gradient in the Cenozoic rocks and having a thermal conductivity from a lower end section. As we go farther down into the Mesozoic, we do have some good measurements on the Pierce Shale, although it ranges from about 0.9 to 1.2 watts per meter per Kelvin, and there may be some systematic changes in it. We need to get a lot more information here. The problem is nobody cores the Pierce Shale. They just go blasting through there because they're headed for the Bakken Formation at about 3 kilometers, 4 kilometers down. So the red numbers indicate the rocks that we've actually measured conductivities in. Now as we get into the Paleozoic, we're getting the rocks that we have good access to in the core library. And then going deeper, we have more rocks all the way down to the basement. So we have quite a number of samples, a pretty good idea of what's down there. And the way we apply it is to look at all the bottom hole temperature data throughout the basin. This is just a shot of all the wells that are out there. And we have bottom hole temperatures in these, and we have core samples from most of them. Now here's a plot of all of the bottom hole temperature data versus depth. And I also have up here temperature logs in 5 deep wells. You can just see them a little bit on the left-hand side, and they're in different colors. And then I have a second order fit to our T-strat calculation, which seems to give a very good, accurate representation of what the temperature would be. This is tied into one well that was drilled by Shell back in the 1980s, and for which we have a pretty good deep temperature log. Now this is a very characteristic scene. You see the bottom hole temperatures are almost in every case lower than the actual temperature that's measured in the well. And most of us who work with this know the reason for this is mud circulation. You tend to heat the top of a well and cool the bottom of a well, and you almost never get an exact temperature measurement there unless you were able to come back a long time after the well has come to thermal equilibrium and then get a measurement then. So one of the things we're trying to do is to use as much information as we have to come up with a scheme for correcting the bottom hole temperatures. And here's our T-strat approach. This is a plot of temperature versus depth. This one well, NDGS 2894, that's a temperature log that was taken back in the 1970s. I will point out that it has a sort of concave upward curvature in the Mesozoic section. We think this is due to a post-glacial warming signal. And this is a case where we're assuming thermal conductivities that we really were not sure about, and we're calculating what the temperature should be as a function of depth, and that's the green triangles on there. And then we have a smooth curve fitted to that. We're comparing that to the bottom hole temperatures within a roughly 10-kilometer square grid around the borehole, and you can see that in the white plot on the right. The borehole is the triangle in the middle, and the bottom hole temperatures that are depicted up there as red dots are from the spots on there. Okay, when we get the thermal conductivities right, this is what we get from the system. Now the bottom hole temperatures are again shown there. The measured thermal conductivities are in this spots where we have the yellow triangles. The assumed conductivities are the green triangles. But in this case, we've got everything pretty much right, and we're getting a very accurate picture of what the temperatures are at depth. And this is just an example of some statistics we've tried to apply to it. Did we get the heat flow right, or did we get it wrong, or something like that? All right, this is the way we will apply it. We'll go to a particular formation that we know can produce water. We'll look at the bottom hole temperature data and come up with a scheme that tells us what the temperature is at various depths in that formation. Now, this is one of the things that one of our students, Anna Kroll, put together using GIS to come up with a map that shows what the temperatures are within the Madison Formation and where they are, what they are. This is a plot of all the Madison wells where the bottom hole temperature is greater than 98 degrees, and this is an isopac map of that same formation. So what we do is we put the isopac map together with the temperature map, and then we come up with a map that's something like this. The contours in this case are depth of the formation, the colors are the temperature. And so then what we do is we try to calculate what's the volume of this, and we calculate how much energy is contained in that particular formation. Now this is just for North Dakota. Again, I'll go back to the final slide here. So this is what we're after, calculating how much energy is in the formation and then attempting to get to the point of how much we can actually produce from it. Okay, that's all I have.
Okay, thanks a lot, Will. I'm going to go ahead and switch over to Joe, our last panelist, before we start taking questions. And Joe, you should have presenter control. And let me unmute you as well.
Does everyone see my screen on AZGS Geothermal Exploration?
Yes, and we can hear you as well.
All right, what we're going to focus on is on this graphic on the right-hand side is step one, is how do we do exploration? How do we locate the site, characterize and select it for next exploratory well? And I'll go into more details as we go along. I thought I would talk about what is and not discussed in this presentation. I'm focusing in on the geoscience aspects of AZGS geothermal exploration for electrical generation. There's some slight modification. The work that we do in AZGS exploration is also applicable to hydrothermal exploration. I'll give some examples of that. And considerations not covered in this exploration discussion, but very important in geothermal development, are land ownership issues, environmental transmission issues, transmission considerations, and power plant and related infrastructure issues, as I think Martin Kay discussed. Okay, my presentation is going to cover exploration. What is that? So I provide a definition. I also talk about the role of the conceptual model, which from my point of view is one of the most important things we have to do as a geoscientist. And I'll talk about the graphic on the right-hand side here in a moment. We'll talk about key AZGS geoscience parameters, regional and local or prospect scales, and then I'll talk a little bit about a project that we're currently undertaking with the DOE, which is seeing if we could calibrate an AZGS exploration methodology. The graphic on the right-hand side shows the continuous conceptual model refinement. Goes well beyond exploration. That's why that yellow box stands below the fifth point. And the continuous conceptual model is one of the most critical things that you could have in exploration, development, and production. It summarizes all your data, and it tells you what's going on in a documented format. And that's extremely important for geothermal activities as well as any other science endeavor. And the last thing I want to point out is this factoid that's on the slide presented below in blue. And that's exploration is a continuous data integration and iterative process. Okay, the definition of geothermal is basically we're locating and addressing where is the geothermal system, and in this case we're looking for one that's capable of electrical generation. The goals of an exploration project is try to identify the potential size, its depth and aerial extent, and the nature of the geothermal resource. Are we looking at a binary or a flash system? What type of resource do we have, steam or hot water? What's the reservoir rock? Permeability type, is it porous media or fractures? And where is the permeability if we're looking for hydrothermal? In AZGS, we don't want to find the permeable portion of the system. We want to find the low permeability and dry portion of the system. And I'll explain that a little bit further as we go along. And then I want to point out that exploration ends with the discovery well, and then the development begins. But the same techniques that we use in exploration will also be used in development and production work. Here's an example of a part of a conceptual model that comes out of our calibrating the EGS methodology project that we had. This is a plate that summarizes the generalized all the data sets we have. That is for this particular project. The generalized geology, the seismic reflection profiles, the resistivity determined by MT, thermal data. These are all temperature data, gravity magnetic results, and P-wave velocity. And by summarizing the data here, all the team members that we have can independently review this and provide their input, and we can generate an interpretation of what's taking place. Okay, for EGS exploration, the key parameters from the point of view of ultra-rock are temperature, rock type, and stress. Ideally, we like to see temperatures between 250 and 300 degrees C. The rock type, we like to see brittle rocks, for example, granite with pre-existing fractures. And the stress regime that we're looking for is a tensional environment. I should point out that the technical work presented in this presentation on the Dixie Valley Geothermal System and EGS Exploration Project was funded both by the DOE and Ultra-Rock Energy. Okay, in exploration, this is an overview of how one goes about it from a strategic point of view. One of the first things you want to do is a literature review. It's the lowest cost activity you can take place, and it provides quite a bit of information. We want to look at the geology, the geophysics, the geochemistry, the hydrology, and any subsurface data we may have with respect to temperature grain holes, swim holes, and well data, and the related lithologies that exist in the subsurface. Then you want to do some type of field reconnaissance work on your highest priority prospects. Now you're starting to focus in on where exactly you want to conduct your exploration work. Once you've focused in on your high priority prospects, you want to do exploration surveys, which are designed to site temperature grain holes. And the temperature grain holes will be at variable depths, depending on what type of environment you're in. Sometimes a 2 meter or 1 meter or 3 meter temperature survey in an environment like the Basin Range is actually the same type of survey in the Cascades. The high Cascades in Oregon, Washington, and California won't do you any good. And then you want to do more detailed exploration surveys to actually site your swim hole and well. As you go through each stage here, you're getting more and more data on a smaller and smaller piece of property that you've been looking at. Now, let's go through the case history. In our particular project here, we used the Dixie Valley Geothermal System in Nevada as a field test site because we had a considerable amount of data with highly characterized geothermal system in the Basin Range, has a significant amount of geoscience data and well data that is all in the public domain. And the type of well data that we had available to the project consisted of lithology from 22 wells, bottom hole temperatures from 26 wells, temperature depth profile from 10 wells, and 9 temperature grain holes. The project is located in fairly central Nevada, And in detail, the project area itself is 2,500 square kilometers. And what we're doing is focusing in on the well field itself, which is shown here in red. And we call that our calibration area, and that's approximately 170 square kilometers. We started with a regional structure. This is the state geological map. The Dixie Valley geothermal field is shown by the red star. It's producing an anomaly about 60 megawatts of power. And one of the things that we recognize is not only do we have a northeast-southwest trending grain here, but the mountain range itself is broken up in a number of places, and that happens to coincide where you have north-south structures coming through the range, and these north-south structures are regional in extent. We've looked at the induced seismicity data for the last 100 years or so, and we found that there was a major induced seismicity structural trend right here, which corresponds with these geological map faults right here. That gave some additional corroboration to our concept that the north-south structures played an important role in the geothermal system here in Dixie Valley. We also want to identify what was the stratigraphy that we were dealing with, because one of the things that we are looking for are brittle rocks. So we subdivided the overall stratigraphy in this project area into seven major stratigraphic units shown here. And I won't go through the details of this, but we will basically want to have a map that we could identify what was the lithologies that we were targeting for potential EGS. So one of the things that we did is take the literature. There was a detailed structural map that was generated by Smith and Blackwell in 2001, and that's shown here. And their structures are shown in purple. Yellow structures come from the USGS and state databases, and the faults that we identified, the north-south structures, are shown in black. We cross-correlated the structural map with the shallow thermal anomalies that were identified in the area shown as red blobs. And what we found is where the north-south structures cross the northeast structure created by the basin range faulting, we had both the compression and dilation zones, and those compression and dilation zones correlated to the shallow thermal anomalies. And we hypothesized that the shallow thermal anomalies were coming up into the dilation zones. We also took it a step further. We had some helium and isotopic ratios, and it turns out that all the available raw data to the project, all the producers occur in dilation zones. It's discussed here in this text area, and show a magmatic signature, and that's also the signature of the reservoir. All available injectors either occur in a dilation zone or other structural zone, and most of the non-producing subcommercial wells are occurring in compression or other structural type zones. So that thought to give us credence that we were understanding what were the structural controls in this particular project area. And this slide shows the correlation that we were able to do based on the limited amount of information that we had on the geologic formations, the stress, and structural zones. I'll just briefly describe what this is. We have well type. Across the top, we have well type, the well ID number, the permeable interval that we identified in the well. What was the formation that was permeable? The bottom hole formation could be different. The stress conditions, and here we're looking at the horizontal minimum stress. And what type of structural zone was it? Was it a compression, dilation, or other type of zone? And the well types we looked at were injector, subcommercial wells, and dry holes. And given the limited amount of information, as I mentioned before, the injectors occur in dilation zones. The subcommercial and dry holes occur in compression zones. And they also turn out to be in this TR formation, which is a shell, which is not deemed ideal for EGS exploration work, and it also turns out to be not critically stressed, which is not favorable for EGS. Then what we did is we took the sum total of all our information and created favorability and trust maps. Many of you may be familiar with favorability mapping. We took it a step further in that we recognized that we could have a favorability map, but without understanding the quality of the data or the reliability of the data that went into making that favorability map, you only have half the picture. So we created what are called trust maps, and I'll explain those here in a moment. Favorability was determined as a function of lithology, temperature, and stress. Those are the three key parameters that we're looking for. And stress was further broken down into 4 different subparameters, which involve dilation, compression, fault orientation, structure present, and Coulomb stress change. And we did this at a scale of half a kilometer by half a kilometer by half a kilometer, and from 1 kilometer above sea level to minus 4 kilometers above sea level. We determined what the weights were for the different factors that we were looking at, and we arrived at all this by taking an internal poll of team SMEs, those are our subject matter experts, and using the average of these input values. Since this slide was created and these series of maps were created, we underwent a DOE go, no-go decision point review. And one of the things that was mentioned that we should take a look at trying to come up with another way of determining favorability and trust. One aspect of this project I haven't mentioned is that we're doing quite a bit of statistical analysis on all the data, and simply we're looking at a way, seeing if we can determine a way that we can determine favorability values, trust values via statistics, and not through polling the subject matter experts. That work is in progress and won't be discussed today. So the favorability values were determined by the following equation. A favorability value, or FV, equals D sub O, which is the favorability value of a cell's geoscience parameter times the weight of that parameter. And we did that for all the parameters that we were looking for. Data trust or reliability maps, as I mentioned before, were produced in a similar fashion with the values ranging from a 5, the highest value, and that's for hard measured data. If we had inferred values, that was a 3, and everywhere we had no data, that was a 1. Lastly, these are 2 examples of favorability maps and trust maps. We refer to as favorability trust pairs. And we show at the top figure the favorability on the right and the trust on the left, and for a depth slice at 1 kilometer below sea level, and the one on the bottom is for 2.5 kilometers below sea level. The weights for the key parameters of temperature, lithology, and stress are shown here that we use in this particular formulation of these maps. And that summarizes my presentation. Tim?
Hey, thanks, Joe. Sorry, I was getting off of mute there for a moment. Let me go ahead and switch back to off here. And I want to So we'll go ahead and open it up to questions at this point. I'm going to go ahead and unmute all of our speakers so that they can take questions. I do want to thank all of them, first of all, for taking time out of their busy schedules here. I know everybody is swamped, but I do want to thank them for the informative presentations as well as their timeliness in the presentations. Do we have any questions? I'm not seeing anyone's hand raised or anything typed in. Take a moment, think about it.
Tim, this is Joe Iovenitti. I may lose you. My phone is going out, so once that happens, I'll call you right back.
Okay. All right, we have a question.
Joe, this is Lee Allison. On one of your slides there, you showed the seismicity, and you had natural and induced seismicity, but in parentheses you said most mine explosions. Could you clarify the difference Were any of those earthquakes induced, or what did you mean by induced? I don't think of mine explosions as being induced.
Well, Lee, simply our seismologist disagrees with that interpretation, and the seismological community believes that mine explosions do create induced seismicity, and that's what was presented in that slide. Commonly in geothermal today, the common thought is induced seismicity due to some type of a production activity. But it's more than that. You know, you have induced seismicity created by dams and in mining operations. And part of that is what's shown on that graphic.
For a second there. Joe, I guess I was just trying to clarify that my understanding induced meant you did something that would generate an earthquake, whereas a mine explosion is just being recorded as if it's an earthquake because it's a seismic event as opposed to having induced one. So I just want to make sure I understand, because I know there's many controversies over seismic activity versus what I would consider man-made.
Right. Let me call in right now, so my phone's going to go out, so I don't want to lose you in the middle of my explanation.
Okay, fair enough. Thanks.
Well, while we're waiting for Joe to call in on another line, do we have any other questions? Questions on how this could pertain to your Year 3 statements of work? Questions to any of our tech team? Questions to the panelists? Okay. I have a question. Hang on, Joe's back on the line. So, Joe, do you want to?
Right. Let me address Lee's comment again. As I mentioned, the induced seismicity covers more than just what is created by geothermal production or production activities or injection activities. You have induced seismicity caused by the weight of water on the earth in the dam environment. And seismologists also refer to seismicity recorded from mine explosions also as induced seismicity. So induced seismicity, in the broadest sense, is any man-made event that created a seismic, any man-made activity that created a seismic event. Does that answer your question, Lee?
It does, and it's a surprise to me, because I thought I would have expected a differentiation between something like injecting water or filling a reservoir versus to be different and induced versus something like setting off an event that actually creates a seismic wave, and call that man-made, but treat that differently. But if that's the definition, that helps me a lot.
Yeah, and I'd also, Rock, and you may want to look at some of the papers that have been presented by our structural geologist, Trenton Kozios at Stanford or the GRC. He coined the term injection-induced seismicity to specifically relate the induced seismicity created by injection activities. But again, induced seismicity is much broader scientifically than just injection-related or production-related activities.
Okay, we have a question from Vikram. Pardon my pronunciation, but you are unmuted. Go ahead and ask your question. Vikram, are you there? Are you muted on your end? Okay. No questions? All right, well, if there are no other questions, we'll go ahead and let everyone get back to either traveling or work. Thank you all for your time. Just want to let you know that we had near 100% attendance, so thank you all. Appreciate it. And if you have any other questions for any of the panelists that might come up later on, just shoot me an email and I'll get that to them. And we did record this, and we will be posting it on the stategeothermaldata.org site as well as a PDF of the presentation. So, thanks again.